In this video, I want to define an eigenvector and show how to compute them. Let's let A be an n by n matrix, so we do need a square matrix. I then want x to be a non-zero vector in Rn. We then say this is an eigenvector if A times x is equal to lambda x for some scalar lambda. So we call x an eigenvector if multiplying by A is the same thing as just multiplying that vector by a number. And we say that lambda is the corresponding eigenvalue. And we'll deal more with eigenvalues in a later video. Here I have a matrix A and a vector U, and I want to know, is U an eigenvector of A? So what I want to know is A times U equal to lambda times U? Well, we know what A is. It's 3, 4, -1, -2. And we know what U is. It's -4, 1. And so we just need to multiply these. This would be a -12 plus 4 is -8. The second row, +4 minus 2 is 2. And we can see that this is 2 times my vector u. So yes, it is an eigenvector. I now want to know, is V an eigenvector of A, where V is 2, 3? So once again, I want to know, is A times V equal to a number times V? So we have our matrix A and our vector V. So let's multiply them and see what happens. Multiplying the first row gives me 6 plus 12, which is 18. And then the second row is -2 minus 6 is -8. And this is not equal to a number times V. To get from 2 to 18, I would need to multiply by 9. However, 3 times 9 is not -8. So this is not an eigenvector of A. Now that we know how to determine if a given vector is an eigenvector, how do we find an eigenvector? We need a value of x such that ax is equal to lambda x. Well, I'm going to rewrite this as ax minus lambda x equal to 0. I then want to write ax minus lambda ix, where I is my identity matrix. It doesn't hurt anything, it doesn't change anything. And it's going to allow me to be able to factor out my vector x. We can only factor out a vector x if both of these are matrices. Before, lambda was not a matrix, but lambda I is. So now I can factor this out. Now, I just need a non-trivial solution to this equation. I do have a homogeneous equation. A trivial solution would mean x is all zeros, but my definition of an eigenvector is a non-zero vector x. So I need another solution, in particular a non-trivial solution to this equation. So let's do some examples. Here I have my matrix A, which is 2, 1, 1, 2, and I know my two eigenvalues are 1 and 3. And I want to find the corresponding eigenvectors. So I'm going to start with 1. We need A minus lambda I. Well, whenever we actually think about what lambda I is, so as a quick side note, in the 2 by 2 case, this would be lambda 0, 0, lambda, so I'm just subtracting lambda from the diagonal, and this is going to hold for higher matrices too. So I have 2 minus lambda, so 2 minus 1 is 1, a 1, and then 2 minus 1 is 1. Reducing this matrix would give us 1, 1, 0, 0. We can then write my equation. This is x1 plus x2 equal to 0. That comes from this first row. Solving for x1 gives me minus x2. When I write my vector, I'm going to write x1 and its equation. x2 is a free variable, so I'm just going to write an x2. Factoring out an x2, I get negative 1, 1. So my eigenvector for this particular problem will be negative 1, 1. So this is the eigenvector corresponding to the eigenvalue of 1. So I found the eigenvector corresponding to 1. Let's do it again for 3. Once again, we need to start with a minus lambda I, which means subtract lambda from the diagonal. 2 minus 3 is negative 1, 1, 1, and 2 minus 3 is negative 1. When you reduce this matrix, you get a 1, minus 1, 0, 0. This first row tells me x1 minus x2 is equal to 0, or x1 is equal to x2. When we write our vector, we write the equation for x1, and then x2 is a free variable, so I'm just going to write an x2. Factoring out the x2 gives me just a 1, 1, so this is my eigenvector corresponding to lambda equal to 3, 1, 1. So now I have 2 eigenvectors for this particular matrix. Let's do an example of a 3 by 3 matrix, and this time I know my eigenvalues are 1 and negative 5. Let's start by looking at lambda equal to 1. This means subtract 1 from the diagonal. Negative 4 minus 1 is negative 5, 1, 1. 2, negative 3 minus 1 is negative 4, 2. And then 3, 3, negative 2 minus 1 is negative 3. We then need to row reduce this matrix. And when we do, we get 1, 0 minus 1/3 for the first row, 0, 1 minus 2/3 for the second row, and 0, 0, 0 for the third row. My equations are then x1 minus 1/3 x3 equal to 0, and x2 minus 2/3 x3 equal to 0. Solving for x1 and x2 gives me x1 is 1/3 x3, x2 is 2/3 x3. So when I write my vector, I write the equation for x1, that's 1/3 x3. The equation for x2, that's 2/3 x3. And then x3 is my free variable, so I'll just write x3. We can factor out the x3. I'm left with 1/3, 2/3, 1. So my actual eigenvector will be 1/3, 2/3, 1. And in reality, it's either this or any multiple of this. So it is common to multiply through by the common denominator to get rid of the fractions, so that this eigenvector corresponding to 1 will be 1, 2, 3. I now want to consider the case lambda equal to negative 5. When I subtract negative 5 from the diagonal, 4 minus negative 5 is 1, 1, 1. 2, negative 3 minus negative 5 is 2, and then a 2. The last row is 3, 3. And negative 5 minus negative 2 is 3. So this reduces to the first row being 1, 1, 1, and the other two rows being all zeros. Therefore, my equation is x1 plus x2 plus x3 equal to 0. Solving for x1 gives me minus x2 minus x3. When I write my vector, I write the equation for x1, which is negative x2 minus x3. x2 is a free variable and x3 is a free variable. We're then going to split this up. I'm going to look at all the terms with an x2 in them. That's a negative 1, a 1, and a 0. And then all the terms with an x3 in them, which is negative 1, 0, 1. So this one has two eigenvectors, minus 1, 1, 0, and negative 1, 0, 1.